peak, right? 12, do you know your chemical shifts, right? Do you know those regions we talked about for NMR, right? Aliphatic, next to an oxygen, or next to the ketone, next to the oxygens, vinylic, benzene rings, and aldehydes. You got to know those regions as well, okay? Can you explain why, if I gave you this, which one of these is more shielded or deshielded? And why? Fluorine's more electronegative. It's going to pull away more electron density. That's going to cause this proton to be more deshielded, right? Can you make sure you can explain that? 14. Do you understand what chemical shift is? Right. That's just where the peaks come out. Shielding, J coupling. Right. We know coupling constants. How things split. And how can you tell, right, if you have the same compound has the same molecular formula, it can have a completely different splitting pattern, right? Are you able to use NMR to determine the structure of a simple compound? We'll work on that today. Can you use carbon-13 data to help determine the structure of a simple compound? So we haven't talked specifically about carbon-13 yet, but we'll do it right now. So it's the same idea that we've been doing. Right? Carbon-13 is the same idea as proton NMR. All we have to ask ourselves is how many different chemically non-equivalent carbons do we have? Right? Chemically non-equivalent different carbons do we have? Right? So in this molecule, how many do we have? So let's just number. Well, let's take a look at this and see if we can figure it out. First thing you always want to ask yourself: is this molecule symmetrical? No. It's not symmetrical. I'll make a difference. Are these two carbons the same?
Yes.
Yes, so let's just say that's one. Is this one similar to anybody else?
No.
No. Okay. Is this one similar to anybody else? The same as somebody else?
No.
No. Is this one?
No. No, because it's close.
And always think about where it's at. If it's going to be exactly the same as another carbon, it has to be the exact same chemical environment. Right? About this carbon?
Yes.
Different? Yep. About this carbon? Same as what?
Same
Is
as
it symmetrical? Is this carbon closer to this isopropyl than this carbon?
No.
So it has to be different. Is this carbon different?
Yeah.
It has to be. About this one?
Yeah.
Is this carbon different?
Yes.
This one? So 10 different carbons in this molecule. 10 different carbons. But it's the same idea as we did the protons, right? Find the ones that are not the same. If they're going to be the same, they have to be some sort of symmetrical molecule, right? We said right off the bat, this molecule wasn't symmetrical. If it's not symmetrical, right, you shouldn't see a lot of carbons being the same. So we'd have 10 different carbon peaks here. Yep?
Doesn't mean for every unsymmetrical compound, we don't have the same carbons for anything.
No, because these two are the same.
Oh.
Be careful, yeah, we're just, you gotta analyze each one individually. Yep?
Can the ones be different because one of ones is closer to a methyl group?
Can this bond rotate?
Yes.
So you can always rotate about that bond. So they're the same. Yep, so that's a tough thing to see, right? Remember, we got to remember some 3 dimensions.
You wouldn't be able to?
Yep, we can't rotate about pi bonds, all right? Promise.
Why 6 and 7 are the same?
6 and 7. 6 and 7?
No, 5 and 7.
5 and 7? How far away is 5 from carbon 3?
2,
2 bonds. How far away is carbon 7?
3.
3. So it's different. It's a different chemical environment. Right?
Well, what's your like 5? I mean, difference between 5 and 3 is like 4 bonds, and then from 7 to 3 is like 5 bonds. Are they gonna be the same then?
Well, they're different. They're not very different. They'll probably have very similar frequencies, but they're still different. Right? They're still different. So what if I gave you well, this molecule, how many different carbons do I have here? Are these two carbons the same? As you know. Are these three carbons the same? Yep, so they all be one. Is this carbon different than anybody else? Well, this one. Yes? This carbon.
Yeah.
This carbon. Does everybody see how this is different? What does carbon 5 have bonded to it? 2 methyls. Carbon 3 has bonded to it, a methyl and a terbutyl. Is this carbon different than this carbon? Can you rotate about pi bonds? So this is always going to be next, this carbon is always going to be next to carbon 4. Right? Because we can't rotate about pi bonds. So that'll be different, and this will be different. Right? Can we rotate about this bond? Right? If you rotate a pi bond, you break it. Can't rotate about pi bonds.
If a torpedo was on 6, then it would be...
Yep, so then if I did this, now how many different carbons do we have? Are there any of these like carbon 1 though on this molecule? Are these like carbon 1? Yep. This carbon? Is there anything else like carbon 2? So you see this molecule right away, you gotta say, I see symmetry. Right? Carbon 3? Is this just like carbon 3? Are they the same?
Yeah.
This carbon 3 is a terbutyl, this one's a methyl. Terbutyl and methyl, they're the same. 4.
So symmetry has to go that way.
So, I mean, either way, you can think about symmetry. It's symmetrical. Yep.
Same thing on both sides.
Same thing on both sides, right?
It would be symmetrical, but it wouldn't be. It would be the same because it'll be symmetrical this way, but not symmetrical.
Yeah, it's symmetrical. One. It's starting to make sense for these carbons. It's just the same as the protons. Very similar to the protons, except you got to take into account carbons that don't have hydrogen bonded to them, right? Okay. So should we work on some NMR problems now with bigger problems? We ready? Questions on this carbon? We gone through our list now? Like maybe we haven't quite got through it. And there's also a table for carbon 13 NMR as well. But it's the same idea. Carbons that are bonded to, which one of these you think will be more de-shielded? These two carbons right here. Which of those carbons do you think is going to be more de-shielded? Right, it's going to be way farther downfield. So the carbon scale is just bigger. It goes from 200 ppm to 0. So that's the only difference. But the same ideas hold true, right? Things are, if you're a carbon bond to an electronegative atom, you're going to become de-shielded, right? They push downfield. So the same ideas. Okay? All right. Who has questions? Yep.
So in this one that I'm looking at right now, it has the C13 NMR with it.
Yep.
And I'm trying to figure out how to make, how to think about that while putting together the molecule.
So we probably won't give you a problem like that, but I can show you how to do it. So the C13, what did it give you for shifts?
17.6.
So C13 NMR. Did it give you a molecular formula?
Yeah, C6H14 all.
C6H14O. So the first thing to do these problems, you have to, remember you got that email from me, you have to do degrees of unsaturation first. If you don't do the DU, right, you can't do these problems. You have to do degrees of unsaturation first. And degrees of unsaturation tells us what?
How many pi bonds
The
or
number
rings?
of pi bonds and or rings. Alright? How do we calculate this? It's equal to the number of C's minus H over 2 minus X over 2 plus N over 2 plus 1. And what does X equal? Fluorine, chlorine, bromine, and iodine. Right? X is the halogens. Right. Okay. So what's our degrees of unsaturation for this molecule?
Zero.
0? So do we have any pi bonds or rings in this molecule? No, we do not. What number is this for you, Lindsay?
17.
Okay. No rings, no pi bonds. What else? So what information did they give us? C13, they told us what?
17.6. 26.5. 38.7. And 73.2.
Right. So we have 4 different types of carbons, right? 4 different types of carbons. Did they give us any other information? What
Yeah,
else
the
they give us?
hydrogens.
They have H proton NMR too?
Yeah.
Okay, what do they got for that?
0.91. 1.17. 1.48. And 1.65.
They don't give us any
Yeah, I was going to
Yep.
go down. And 6 hydrogens,
for which one?
top one. Going down.
6H?
Yep. It's a doublet, and it's 7 hertz. And that one's 6 hydrogens, it's a singlet. 1 hydrogen, singlet, and disappears after D2O shake.
So it's probably broad. Okay.
And the last one is 1, it's a septet, and 7 hertz.
7 hertz, right?
Mm-hmm.
All right. That all the information you got?
Yep.
Okay. So to start this problem, first thing we did was degrees of unsaturation, right? So we know there's no rings or pi bonds. Right? No rings or pi bonds. So our molecular formula, I'm going to draw that right here. So redraw C6H14. Okay, good. Which of these 3 peaks should we start with? 4 peaks. So how many different protons do we have in this molecule? 4. This molecule is probably symmetrical. If you look at it, if you have C6H14, how many? 14 hydrogens is a lot, right? If you only have 4 peaks, that should probably tell you something about maybe the molecule being symmetrical. All right, so if you have a lot of hydrogens ever, think, and there's only a few peaks, think symmetry, right? Think symmetry, right? Look back at these examples. Right, these examples, they'd have 1, 2, 3, 4, 5, 6, 7 different hydrogens. That molecule right there. Right, so if you only have 4 peaks, and you have a lot of hydrogens, right? Less peaks, more hydrogens.